you try to share your screen?
Yeah,
I'll read off your bio. Jerry began his career as a surveying instructor in 1979, retiring for the second time in 2020. He taught at the University of Wisconsin, Platteville, Purdue, Penn State Wilkes-Barre, and Madison Area Technical College. And he's presented workshops and seminars since 1984. He's also worked with the National Geodetic Survey, Bureau of Land Management, Wisconsin DOT, Wisconsin Department of Registration and Licensing, and done consulting. And we're happy to have him as a regular contributor here on Mentoring Mondays. The link to his bio there is in the chat, as well as a link to the Mentoring Mondays page in Jerry's website. And hey, that's a good looking diagram there, Jerry. So your share screen is working at this end.
Okay, good.
And Frank's just entering. So give about 10 seconds and Frank should be joining us.
Okay.
And I'll be, this is Rob McMillan. I'll be monitoring the chat today and trying to keep an eye on things. Trent is on an aircraft heading back to Nevada. I don't think he actually lives in Nevada on the weekends. I think he only is there for business during the week. And otherwise he's on golf trips or family vacations or who knows what. But I don't know if he'll show up before we conclude today. But if not, you'll get to see him next Monday. All right, with that, Jerry Mahoon.
All right, thank you. I don't know if anybody's we've had a chance to download. There've been quite a few visits to the Mentoring Mondays webpage on my website, whether you've downloaded the handout for tonight or not. But it starts out with about 4 pages worth of equations, just some general equations that we use to solve trigonometry problems and basic surveying Kogel problems and that type of thing. So if you haven't downloaded that, you'll want to do that. I'm going to go through some of those problem solutions tonight, talk about some of the geometry, trigonometry solutions to problems. And I ask you for feedback. I'd like to get some feedback from the audience as far as how they would approach solving some of these problems, what some of the logic is. I will have complete solutions for most of the problems posted on the website in a couple of days. And I did post 4 more problems up there, which are also trigonometry type problems, applied trig problems. For about 10 years, until relatively recently, I used to do the problem corner, write the problem corner for the Wisconsin Society of Land Surveyors newsletters. So I really get into this kind of stuff, and I love solving these types of problems, particularly ones that I can compose that you can't solve necessarily easily using the pre-canned software or a CAD program or that type of thing. Before we get started, originally the description for this session was an open session for anyone who had questions about any questions concerning the exams, problems on the exam and that type of thing or coverage. Do we have any questions about that type of stuff before I dive into this stuff here? I don't know if that's somebody. All right, well, we'll get started. If anything does come up, feel free to break in or raise your hand in the comments area there, or pipe up. Or if I'm going too fast, let me know. Also, I do have my contact information there, so that you can contact me afterwards if you have any questions. Let me see, make sure, I don't know if I've got the chat view open here. Anyway, well, so let's go through some of these things. Where this all started with was Sean Sear. I think I got that right, didn't I, Sean? sent a question and about 2 problems from Van Sickle's review book, asking about the way to solve those particular types of problems. So those are the first 2 problems we're going to be dealing with here, or variation on them. And I've got a couple of other trigonometry problems, which we may or may not get to, depending on how this stuff goes. But a couple of things that you want to keep in mind. And I also work with the CST people, and I've been reviewing some of their exams and stuff for the Certified Survey Tech program. And one of the things that you got to be careful of is whenever you're dealing with problems that are computational, that I make a big thing out of significant figures and how accurately to depict numbers or how accurately to calculate types of things. One of the biggest problems we run into with students doing calculations, particularly trigonometric calculations, is rounding. People have a tendency to round, like say 3 decimal places for a lot of things. And as a consequence, when they finally get to the answer that they're getting to, there's been a lot of cumulative rounding error in there. So it's always safer to carry more digits than necessary and round when you get to the end. And just realize that when you come up with your answers, and then you've got the ones to pick from that are presented there, they may not exactly match, and that could be because of rounding. So a lot of times you have to resort to picking the ones that are the closest to your computation. So keep that in mind. If you do a calculation, you don't come up with the exact same number of what they've got, it could be the difference in who's carrying how many decimal places when they're doing the calculations. And a lot of times, sometimes, and I don't encourage you to go through life like this, but a lot of times you can use reasoning to eliminate some of the answers entirely from the choice, so that you can sometimes work your way down to the right answer without having to actually work your way through a relatively complex problem. We'll see an example of something like that tonight. But sometimes you can narrow it down to just a handful of choices, maybe 2 choices instead of 4. So if it does get to the point where you're running out of time and you got a guesstimate, you increase your chances of guesstimating. A real common type of problem is like this one here, where it says, if you're taping with a steel tape below standardization temperature, will your distances be too long or too short? And they're generally given a couple of distances, some that are longer, some that are shorter. Well, when you realize that when the tape shrinks, your distances that you record are actually too long, just the opposite the way most people think about it, you could automatically throw out, say, maybe 2 of the answers and narrow it down to 2. So, look at the answers, and sometimes you can reason out from what's presented, there's choices, which ones make sense and which ones don't. All right. The first problem that Sean had sent in was one that initially had me a little confused, and this goes back again to the wording of questions and that type of thing. And then I played around with this for a while, and I finally realized exactly what was being asked. And what we have here on the right-hand side is an original alignment of a street. It's a tangent section into a set of 3 curves, back-to-back curves, reverse curves. And you're given the curve information for each of those curves, the central angle, long chord length, and radius for each. And the problem says that the center of the second middle curve is going to be moved at a specific distance and direction from its original location. However, what's going to happen is the radius of this curve is going to be kept the same. These 2 points are going to stay where they are, but their radii are going to change because the whole alignment's going to get shifted. Now, they're maintaining parallelity and perpendicular conditions. And remember, what makes curves tangent curves is that they maintain either a right angle relationship between the radius here and the tangent coming into it or going out, or they're collinear, that the centers of the curves and where they intersect are all in a straight line. So this point's going to stay, this point's going to stay. That means if we shift to here, we're going to create a new radial line connection from here to there and from there to there. So if we draw a sketch, whoops, another way, this is what's happening to the alignment. And once we see that happening, then we can start to see, how we're going to start solving this type of thing. So you can see the light gray is where the curve, where the alignment situation was. The red is where the new curve geometry is. And you can see that the eye angles change, the length of the curves change, all the geometry about those curves change. So the first question that's there is, what are the new central angles for the three curves? And the choices that you're given, typically on an exam, you're going to have a couple of choices, A, B, and C. So we have to figure out what are these central angles that are in here. Well, the question is how do we start computing those? Well, and there's a couple of approaches to them. Some have advantages over other advantages. We could set up a set of triangles and say, look, what we know is we know the length and the direction here. So we know this side of the triangle. We know the length here, that's the original two radii added together. We know the original direction of that line, so we can figure out this angle in here. So you have distance, angle, and distance. You have three parts of a triangle. You can start to solve other parts of that triangle using law sines and law cosines of that. That's one approach to do it. The problem with using that approach is you get this really long, narrow triangle. And when that happens, rounding error becomes pretty substantial if you round off the angles too much, because this is going to be just a little teeny tiny angle. Another way to do it is by coordinate geometry. That is, if we can come up with coordinates of these points here, all those points, and then we know that the eye angles are simply the differences between the directions of those respective radial lines. So that's what we're going to do here. And what I did was using an approximate, I just guesstimated coordinates for this point right here, and then using the original direction and the two radii, do a forward calculation, you get the coordinates there. And then using this direction that was given and the two radii, we can get these coordinates here. And that's really all we need down here is these three coordinates. Once we're up here, because we know the distance and direction from this origin to this origin, we can compute the coordinates of that guy right there. Now it simply becomes a coordinate inverse problem. We inverse between coordinates, that gives us directions and lengths of lines. So if we inverse, we get a new distance and direction for these two lines here. Now, the eye angles that are simply this angle here, and this angle here. So if we take the direction of this line, say the azimuth of this line, we subtract the azimuth of this line from it, that gives us that angle. If we take this azimuth and this azimuth, find their difference, that's that angle right there. And we can very quickly compute those angles, okay? So you can see that's a little bit of a lengthy calculation because you have to go through computing coordinates and then inversing coordinates to get the new directions and to compute all the angles. Is there a simpler way to do that? Well, yes and no. Okay, remember what I was saying before about logic and reasoning? Let's look at our answers here now. The answers that they gave us, they're not exactly identical to what we came up with number-wise here, but that's because of rounding error. I carried a lot of digits on this, but those are the closest ones with respect to that. Now, let's use logic or reasoning. For an alignment, if we're going to go from this tangent to this tangent, we have to go through the total of this eye angle, and this eye angle here. This is to the left, this is to the right, this is to the left. If we take left angles as negative and right angles as positive, that tells us the total angle that we have to go through here to get from one tangent to the other one is 51 degrees, 8 minutes. So all we got to do is real quickly, and this is the first thing I did, is I add up all these eye angles that they give us here and see which one gives me 51 degrees and 8 minutes to the left. And it's the first one that does. The other three don't. So just by simply adding up the eye angles that they give you, you can see right away, these three are incorrect. This one is correct. So that's the short way of doing it. Okay. So that's using logic and reasoning with respect to it. All right. How about the radii of the curves? Now remember the second one, the middle one, when its origin was pulled back, it kept the same radius that it had before. So anything that acts to change the radius in here, any of those, curve number 2, we can throw out automatically. Curves number 1 and number 3, however, are going to change. Now, if we did it by COGO, we've got the total distance from here to here and from here to here. If we subtract off the radius of curve 2, that gives us the new radius, new radii of curves 1 and 3. So that tells us that's this guy right down here. And right off the bat, like I say, we could eliminate B and C because they both changed the radius of curve number 2, and curve number 2, by definition, stayed at a radius of 173 feet. Okay, so got that? So, yeah, so we're using both logic reasoning as well as calculation. The long chords of each curve, and you can see this is the problem is a cumulative one. As you compute each piece, the next piece falls into place. And when it asks for the long chords of each curve, now we start to look at the equation for computing a long chord, which is the length time equals the long chord equals 2 times the radius times the sine of half the central angle. So now the calculation becomes even quicker because we've got all the other pieces already. We've got the radii, we computed those in the previous part. We've got the central angles because we computed those in the part before that. And then we could just plug and chug those into there. So we just plug those in there, and which one matches? The very first one matches.
Jerry?
Yeah.
Just so the folks that are taking an exam like this, just the same kind of reasoning that you had earlier,
Right.
just look at that curve 2 and see that they give you 4 different choices, right?
Right.
But curve 2 didn't change. Oh, it changed delta, but it didn't change its radius.
Right, right. The radius didn't change, but the delta did. But again, you can look at them and say, well, which ones make sense? Because these two chords got longer, this chord got shorter. The one in the middle got shorter. Because this eye angle decreased, this one, these increased. So again, you can look and see which one of these meet those conditions and maybe narrow it down to 1 or 2 choices. And
I'd say that the values that they give you to use for curve 2 are big enough that big enough differences that you wouldn't have a rounding error.
Well,
like you could have in curve 1 with the 155, 32, or 48.
Right, right.
Or the same value in curve 3.
Yeah, generally when I design problems like this, I try to make enough of a numeric difference between the similar elements so that when you come up with something, it's not just like something you can get tripped on from a rounding viewpoint. Like if you notice, the central angles for these two are exactly 7 minutes apart. So it's easy to accidentally flip them in here or to write the wrong one in the wrong place. What you'd like to do is when you design a problem, and this goes back to how you write exams and that type of thing, is to come up with numbers that are pretty drastically different in here so that there's no confusion like that. The idea is you don't want to confuse somebody. You want to test their knowledge of being able to solve applied trigonometry problems. And sometimes you guys, think about, sit there, think about. And the other thing I encourage students to do, and not everybody always does this, is to learn how to use the memories on your calculators. Most calculators have multiple memories on them, more than just 1 or 2 or 3 memories. And instead of writing down all the numbers and then repeating that each time you do the calculation, store them in your memories. What you should write down is what it's called in memory. So like I've got an old calculator that uses 2-digit numbers for the memories. I'll say that when I compute R1, it'll be in memory 01. R2 will be in memory 02. R3 will be in memory 03. So all I got to do is recall those numbers instead of rewriting them down and all that. And that saves you a lot of time computation if you do that also, use the memories. Okay, last one, arc lengths of each one. Again, relatively simple, straightforward. We know that the length is equal to the radius times the central angle times pi over 180. And again, we've computed all those other pieces before. It's just a matter of plugging and chugging to come up with numbers. And again, look to make sure it makes sense. The first two get long, the first and the third get longer, the middle one gets shorter. So you want to do a visual check on that to make sure that you're coming up with the right numbers. Again, if you flip these two in here inadvertently, you might find out the different thing is happening there. So again, the closest ones to that, and rounding is a little bit of an issue, but not too much, but those are the ones for that answer. So again, you take this basic problem here, which looks like it's relatively complex to begin with. And when you start to break it down into the pieces and look at it, and a sketch is always something that helps you organize what you're computing, what's being asked for, and how you're going to approach it. That'll help you point out what your logic is. Like when we put the eye angles on here, we know that if we have the directions of these lines, we can get the eye angle or the delta angle, whatever your nomenclature is that you're used to, for that relatively easy, as long as we have those directions. Okay. All right, another problem, the other problem, let's see. Yeah, new centralized, what I said, what else? Dink, dink. Oh, and the bearing of each long chord. So now we not only have to compute the length of each chord, we also compute the bearing of each long chord. And the obvious things you look for is if we're going in this direction here, we know they're all going south and west. So you want to look for the ones that have got south and west for all the chords. In this case, they all do. If you have a north and east one in there, you know that one's not the right answer. But basically, when we compute this, we know that for any tangent curve, the angle between the tangent and the chord is half that central angle. So if we've got this beginning direction here, we know that's 90 degrees there. To establish this direction, then you have this angle here to get into this guy. We can compute this direction then, this direction of this line, and keep on going from there. So it's basically knowing that basic geometry of the horizontal curve, that these are half the central angle, and that angle up here is the same as the angle down here. Draw a sketch. Can't emphasize that enough. Right. All right. The second problem.
Hey, Jerry, before you jump into the second one,
yeah,
something to remember for the students is to be sure that if your calculator is, say, an HP, that you change it into decimal degrees to take your trig functions and your whatever your manipulation is with your angular measurement, and then remember to convert back out, because right. One of the things in developing exam problems is, for example, one of those was 40, I think it was 08 something minutes, right? Minutes and seconds. So if you don't convert 08 to decimal degrees, or the other one was 01, if you don't convert, you're going to be very close, but not quite the value in decimal degrees.
Right.
And so your answers are going to come out close. Now, if the people that are doing the actual exam development are doing their thing very, very carefully in constructing the wrong answers, then those wrong answers that are shown as your choices will be what you'd get if you did something like forgot to
right.
to go with decimal degrees, something along those lines. So keep track of that, contestants.
The other thing I want to point out, and this is I generally spent the first lab period of my intro surveying class talking about calculators. Simply because people spend a lot of money on calculators and don't know how to use them or don't utilize them correctly. There are only a couple of calculators that are allowed on the licensing exam. And one of them is a Texas Instruments TI-30 family, and the other is a Casio FX115 models. And kind of going back to what Rob was just talking about here, the Texas Instruments TI-30X or the TI-30A is about the simplest calculator that you can get that does basic trigonometry applications, trig calculations on it. Sine, cosine, tangent, inverse sine, inverse cosine, inverse tangent. But you've got the conversion keys on there to go from degrees, minutes, seconds to decimal degrees, and decimal degrees to degrees, minutes, and seconds. So you enter the angles in a particular format. On this guy right here, to take trigonometric functions of angles, those angles have to be in decimal degrees. When you take the inverse trig functions of a number to get an angle, that angle comes out to be in decimal degrees. If you want to convert from those decimal degrees to degrees, minutes, and seconds, there's generally a function on here that you have to go through. In this case here, it's a second DD to DMS. If you want to go the other way, DMS to DD, it's this one right here. Now, this is not consistent on the TI-30X family of calculators. Some of them have this type of approach. The others are similar to the Casio FX115. You notice on this one here, it's got a degrees, minutes, and seconds button. So when you want to put an angle in degrees, minutes, and seconds on here, you would type in the degrees portion, hit this button once, the minutes portion, hit it again, and put in the seconds portion and hit it again. It'll show the angle through degrees, minutes, and seconds. Now this one, you can take you can take the trig functions of an angle either in decimal degrees or degrees, minutes, and seconds, depending on how you input it, okay? So again, you got to become familiar and comfortable with your particular calculator, because if you're used to using one of these and your calculator dies and you say to your friend, can I borrow yours? And they hand you one of these, you could be at a loss as to how to do trigonometric functions on there. And like Rob says, the wrong answers, the typical wrong answers will generally be part of the choices there. Because it's, people that don't know how to use your calculator correctly. And also make sure that you're in degrees mode and not radian or grad. If you're in grad and degrees, if you're in radian mode, you'll get a different angle, different results for a trigonometric function of an angle than you will if you're in the degrees mode. So again, figure out where that is and how that displays on your calculator to know which your application is, or what you use it correctly on your calculator. No, my tongue's getting in the way of my speaking. Okay, let's see. I'm kind of all right. Now with that sidebar out of the way here. Let's just see if there's something. Okay. All right. The second problem that was presented is another one of these neat little trig problems. An existing curve between two tangents encroaches onto lot number 4. So here's lot number 4 here. And the curve comes in here and encroaches on here. Even though the tangents themselves come in further, the curve just comes into this area here. And the way they want to handle this is they want to replace this single curve with a compound curve, or a back-to-back horizontal curves, differing radii. And it's going to start at the same place that the single curve started. It's going to be tangent to the northerly boundary of lot number 4. And it's going to have a new PT out here somewhere to intersect. So this is going to take this curve right here, this in gray, and replace it with this one right here. C will be, point C right here will be the PI of the second curve point A is going to be the PI of the first curve. So here's one tangent, here's the other tangent, and then here's the third tangent. So here's where our curves fit in between now. Okay. We know that the original I angle is 71 degrees 50 minutes between the tangents. We know that this line here, this incoming tangent, intersects the northern boundary at an angle of 41 degrees 35 minutes, and that the distance, let me back up a second here, between the beginning of this curve and point A, where it intersects the northern boundary of lot number 4, is 11.77 feet. So from that, basically, we want to compute all the geometry of the rest of the curves. Now, for any curve, in addition to knowing whether it's a tangent curve or a non-tangent curve, we have to know at least 2 geometric elements about that curve to fix it. Just knowing its radius doesn't tell us how long the curve is or what its tangent lengths are or anything like that. So we have to at least have 2 geometric elements of any curve to fix its overall geometry. All right. So when we look at this, here's our sketch. Here's our PC of the first curve, the end or the beginning of the next curve, the point of curve to curve, and then the length of the next curve. We know that these the central angles of both of these together have to equal this right here, because it's going through that total transition from this tangent direction to this tangent direction. All right. So the first question is, what is the radius of the first curve? Okay. So I look at that and say, well, what do we know about that first curve? Well, what we know about that first curve is that this is, because this is these are the tangent lines, this angle in here represents the central angle of that curve. That's one geometric element. The second geometric element is we know the distance from here to here, that's from the beginning of the curve to its PI, that's the tangent distance. So we know the central angle, we know the tangent distance. We can figure out the radius of that curve by substituting it to our equation T equals R times tan I over 2. If we plug in what we know in there and then solve for the unknown, that gives us a radius of 31 feet. So if we look back, and I'll look back at what our choices were, 31 feet were one of our choices right there, okay? We can toss out probably toss out the 52.33 because we know it's not going to be longer than this curve. It looks like it's going to be shorter. All right, now the question is, what's the radius of the second curve? Now this one becomes a little bit more complex, a little bit harder to calculate. Now, we said that we know that this angle, the 2 I angles together have to total this I angle down here. So we know that the central angle of this second curve is going to equal a 7150 minus the 4135. So we know it's 30 degrees, 15 minutes. So that's one geometric element. Can we do we have a second geometric element for that curve? Well, what else do we know? We know this distance here. We know this angle here. We know this angle here, this angle here. Looks like we're short on distances and that type of thing. But if we look at this triangle here, this is called the vertex triangle because it connects all 3 PIs for those curves. So we know this angle. We know this angle, which is the same as the I angle for this one here. And we know this angle, which means we know this angle here. So we have a triangle and we know 3 angles of that triangle. Now, typically to solve any triangle's got 6 parts, 3 sides and 3 angles. To entirely solve a triangle, you need to know at least 3 parts to begin with. And at least, I kind of wandered off the screen here. I don't know why that happened. And at least one of those parts has to be a distance. These 3 angles do not fix the overall size of that triangle because you can come up with parallel lines to this. They'll have the same interior angle, but the triangle will be much larger. What we need to do is to fix at least one side here. Now we know the distance from here to here, from A to the PCC, that's T1. That's the same as this guy right here. the distance from here to here is T2. That's the tangent distance for this curve. Well, we can't compute that because we don't know what the radius is for this curve. So we can't compute T2 from there. So we have to figure out another side of the triangle. So if we had this complete side here, we could say that's to the sine of this, as other parts are to the sine of the other angles, and we can solve the triangle and then get our pieces and stuff. But we don't have any sides outside of this guy right here, or do we? Well, remember that this point right here, PC to the PI, was the original tangent distance for our curve that we had in here to begin with. So if we were to take the radius of that previous, that single curve and its central angle, we can compute the tangent for this whole side from here to here. Once we have that, if we subtract off this, that gives us this side of the triangle. So now we have a triangle and an opposite side, and we have this side and that angle. We can compute this side here as being 45.34 for this entire side here. We subtract off the 11.77, that gives us this side right here, which is the tangent. And now we just solve this equation backwards for the radius, and we come up with a radius of 124.20 feet for the second curve. So you got to get kind of creative sometimes on these and look at, so what do we know and what do we don't know? And solving the vertex triangle is one way of doing it, because we always know that one side of that triangle is the sum of the tangents of the two curves that are involved. And that comes in a handy way to solve problems, solve some problems. It were the long chords for both. Again, once we have the radius and the central angle for each one, the long chords are easy to compute from the long chord equation. 2 times the radius times the sine of I/2 for each one. Okay. All right. Now I threw in a couple of extra ones here. That I've used in some of the WSLS problem corners and that type of thing. And was wondering if anybody tried doing these to solve the problems. Okay, so let me read this one real quicker. A total station is placed on top of a lookout tower. The height of the instrument is 5.2 feet. And zenith angles are measured to the far and near sides of a river at the water, where the water intersects the shore. And those are 2 zenith angles, 115.2206 and 129.1549. And then the horizontal distance was shot between the 2 river points, and they were determined as 225.35 feet. If the river elevation is 841.2 feet, what's the height? What's the elevation of the tower? Anybody compute that? Anybody figure it out? These are this is a story problem. I didn't give you a diagram or a sketch or anything for this. So you have to kind of figure out what's being asked for and what's being provided. I have any takers on this one? Anybody?
Jerry, I had looked at it, but I was having a hard time trying to set it up, as you know, just looking at it.
Yeah, I told I always give problems. I always give problems like this to my students, particularly when we're dealing with declination problems and that type of thing. And it drives them up a wall because there's story problems, and they need to reduce them to a sketch. And my argument is that you're gonna have a client that's going to ask you to solve a problem like this more than they're going to have a client that says if y equals 2x and x is equal to 3, what's y equal to? They don't ask you stuff like that. They ask you story problems that you're asked to try to solve. And a lot of times you got data that's not necessary, it's not germane to the problem. Well, in this case, it is germane. So what you want to do is you want to take and put all this stuff into the form of a sketch. What do you know? What happened? Okay, so let's do this. Let's put our tower up here. Here's our total station located 5.2 feet above the tower. And then zenith angles are measured to the near and the far side of the water. Okay. Later on, the distance is measured between these 2 points as 225.35 feet, and the elevation of the water is 841.2 feet. What we want to know is the elevation up here. Okay. Now, when we put it in graphic form like this, we start to see things fall into place. We have a triangle here. Ding, 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 right? We have a side, 225.35 feet. We have an angle here, and we have an angle here, which means we have this angle up in here. So for this triangle, we have a side and an angle. But we have to have at least one more piece of that triangle, either a length or an angle. So we need either this angle, or this side and this side to start solving for things. Well, there's another triangle. Okay, if we isolate our triangles, if we drop a vertical from here and go straight across, here we have a right triangle. This is 90 degrees. This coincides with this direction right here. Now, if we look at this angle up in here is 51 degrees, 44 minutes, 11 seconds. When we subtract it from subtract the zenith angle from 180 degrees, because this is 90 degrees, that makes this angle 39 degrees, 15 minutes, 49 seconds. Because this angle is 39, 15, 49, this angle here added together is 180, gives 140, 44, 11. Now that we know this angle, and we've got this angle from the difference between these two, we can get this angle down here. So we have all the angles of all these triangles, and we have a side, 225.35. So now we got 3 angles and a side. We can use law of sines. This is to the sine of this, as this is to the sine of this, to get this side of this triangle. Now that we've got angle, 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 side, we can compute V for this side, okay, using our basic trig. And now that we've got that, that gives us the distance here. And if we add that to the elevation of the water, that gives us the elevation to the total station. And if we subtract the total station height from there, that gives us the elevation of the tower. So the idea is to get it into a sketch, but then augment that sketch as necessary. This is a summary of the data that was given. This is the additional geometry that exists, vertical, horizontal, to create another triangle, so we can compute pieces of these triangles together. See that? And then we wind up with that elevation. And again, look at the numbers, see if it makes sense. It should be higher than what the water is at, right? As opposed to lower. Questions on that one?
I got a question.
Yes, ma'am.
Oh, no, maybe I don't. Sorry, I was just looking at your answer before you got all the way to the answer. So I saw the 1095, I was like, oh no, I got it wrong. But then you subtracted. Okay, I'm there.
Yeah, and that's another error. That's in a list of answers, that wrong answer will be there because you forgot to subtract it and that type of thing. So always get, it's attention to detail. Make sure that you compensate for that. All right?
I did get B originally. I just in the last moment, it was like, wait, oh no.
Yeah.
So I did it first with law of sines and got that answer. And then I was looking for how to solve one of the later problems and stumbled on a different way to do it, which I got the wrong answer like 3 times.
Yeah.
And then turned out, oh, I have a math problem that I don't know how to do the math.
All right.
So
another thing I tell students is when you do an exam, don't brute force it. Don't start with question number 1 and make sure you get all the way through question number 1 before you go to question number 2, before you go to question number 3 and that type of thing. Go through, look it over. For one thing, it gives you an idea of what the format is like, but do those that you can right away. Those that you can't do right away, leave till later. And you might discover during the process of doing another problem that, oh yeah, I can apply this to that previous problem. It might jog something in your memory and that type of thing. So be flexible in your approach to a problem, the exam solutions. Don't think that you have to start with question number 1 and finish it entirely before you can move on to question number 2.
Mhm.
Okay. All right. This one right here, it's a relatively simple looking problem. A total station was set up at a point from which 3 of the 4 corners of a square parcel is visible, and distances are shot to those 3 corners. That's all this does. 3 distances were shot. And the question is what's the parcel area to the nearest 10 square feet? Anybody solve this one? This is one of my favorites.
I got an answer that wasn't quite on the list.
What wasn't quite on the list by how much?
30 feet.
30 square feet?
Yeah.
30 square feet, that could be again a rounding or a rounding type thing, depending on how many digits that you carried in that, you know.
Oh, I just kept
So
everything in the calculator. So,
okay, which one did you come up with?
well, D was the closest answer.
D was the closest one. Okay. All right. How did you approach solving it? Just out of curiosity.
Well, this is the one I had to like research how to do it because it didn't come to me immediately. It's you kind of have to rotate it and put it next to itself. I don't know.
Okay.
If that's the way to do it, then that should make sense.
Yes, that is one way of doing it. It's probably the easiest way to do it, but the least apparent one. Because what people want to do right away is when you're dealing with areas and you got distances, what people want to do immediately is start to solve areas of triangles. Because triangles are relatively simple, the most basic type of geometric figure to solve the area for. So you can say, well, I know this side's the same as this side. So I can write both of these areas in terms of that side right there, because they're the same thing. But once you get over onto this side, it's not a triangle. If you connect this with that right there, you've got a triangle, but you've only got one side. You don't have 2 sides along with that unknown side. And it's possible, but you wind up solving a bunch of simultaneous equations.
And that's when I stopped and looked for a different way to do it.
Yeah, and I think you probably wind up with probably three equations and 3 unknowns. Geez, I don't know why I'm drifting all over the place. It's like I'm lost in space here. But anyway, I think what the method that you're referring to is a method that I employed with respect to this. And the key is that this is a square piece of land. If you look at this triangle down here, it doesn't have to be necessarily this one right here, but if you look at this triangle down here and rotate that, a copy of it up to here, so that this side here coincides with this side here because it's the same length, you've now created a copy of that triangle up over in here. Once you do that, then if you connect this point with this point, what you have is a nice isosceles triangle. This side here and this side here are the same. And this side here is 45 and this side here is 45 because that's a 90-degree angle. And this isosceles triangle, these 2 angles are the same. So now you've got all 3 angles are known. 2 sides are known. You can compute the 3rd side using law of sines. Or law of cosines for that matter either. Once you have 4 pieces to a triangle, there's a variety of ways you can solve for it. So now you have this side here. And if you look at this triangle over here now, you have this side of the triangle. You have this side of the triangle. You have this side of the triangle. Now you can use the law of cosines to solve this angle right in here. So that angle in there is 16 degrees, 56 minutes, 29 seconds. So now the total angle here, if we look at this triangle here, this total angle here is this angle plus this angle of 61 degrees. And the area of a triangle is equal to 1/2 the 2 adjacent sides, product of the 2 adjacent sides times the sine of the included angle. Okay, so now since we have the included angle, bink, 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 we can figure out, wow, excuse me, I got back up a second. Now that we've got the two angles here, we've got this angle here and the two sides, we can compute this side right here. And once we have that side there, because this is a square piece of land, then you take and multiply those two together and that's what you wind up for there. So D is what you come up with. What did you wind up for distances for the sides there, Jen?
That's what I got.
206.
You got the same 30 feet off that I did.
Oh, I guess my mistake. I put the wrong answer up in there. Ha! Thank goodness that wasn't one of the exam questions. All right, yeah. So that's I gotta make a note to myself. Error. Answers for number for D. Okay. Now again, that's not the only way to solve this. I mean, one way to solve it is like what we're talking about for breaking up into triangles and solving all those equations simultaneously, but you can wind up getting quite mired in the problem. The other thing, can you use logic and reasoning on this one? Well, I don't know. I haven't tried this one, but if you look at, you know that it's a square piece of land. So if you take the square root of each one of these, so if you take the square root of 115,000, let me just get the calculator out here real quick. Square root of 15,000, that's 122 feet. So you can throw this one out right away because 122 feet along this side is too short compared to these two distances here. You know, you figure it's got to be at least 184.62 squared plus 82.74 squared equals square root 202 feet. And you figure it's got to be at least 202 feet here. So if that gives you about 202 feet, and you see you're in the vicinity of these two guys right in here. So you might be able to reason your way out and say, well, I'm going to toss these two, and it's got to be one of these two. Okay. All right, how about problem E? Anybody do problem E? No takers on this one?
I did it. I got to find my notes.
Do not, when you encounter a problem like this, don't immediately jump in and start solving things. Try to figure out look at what you're asked to be solved and figure out some sort of logic to the approach. How would I approach solving this problem? What do I need to compute? And what pieces do I need to compute for it? Okay. This is a real typical type of problem. We've got old alignments and stuff all over Wisconsin like this, where we've used reverse curves to get around things or go between, say, closing corners on township boundaries and that type of thing, where the old roads used to follow, do a right-hand 90-degree turn and immediately a left-hand 90-degree turn. And now we're trying to smooth those out with either a longer compound curve or a single curve if possible. But in this particular case, the original center line that was in there swung around the wetland using a reverse curve situation. And now they want to replace those two curves with a single curve that comes to the inside of that wetland instead. So the question is given the geometry for the existing curves in there, what's the radius of the replacement curve that would go in it? It would be tangent to the same two incoming and outgoing lines. So we've got this line coming in into the PC, and it's going to start at the same point, and it'll come out over here tangent to this line here. Now I have to provide a constraint of some sort because there's an infinite number of curves that are tangent to these two lines. So we have to do something to fix the geometry. In this particular case, the geometry was fixed by saying this curve had to begin at the same place that the other curves began. So that fixes where the relationship of this point here with respect to the tangents. Okay. So how are we going to start approaching this? I got to work on the focus of my camera because it's just zooming me in and out. And anybody?
I did it. I
Okay,
think.
okay, what would, okay, how'd you approach it?
So I started with drawing a perpendicular to that incoming road that goes down to the center of the first curve.
This way?
And then that gave me like an origin and a direction. I kind of rotated it and thought about it that way. And then there's a diagonal that goes from the center of that curve through the PRC through the center of the second curve. And then it was changing X and Y and calculating things from that, basically.
Okay.
And then it gets sort of messy.
That's why we're surveyors, is because we like messes like that.
But I got answers that were on the list.
Okay, well, good. Because there's some obvious wrong answers on that list too.
Okay.
All right. Any others? Anybody else? Give this thing a shot, or at least looked at it and thought maybe it's time for a career change or something like that. All right, let's look at let me show you the way I approach solving this. Okay. We know that if we extend this line straight through here, where it intersects here is going to be where the PR is for the replacement curve. Okay. So if we can get that point right there, boy, we got it made. All right. So we know that this angle here, the I angle here, has to be the sum of this angle plus this angle here, the central angle here and the central angle here. This is an angle to the right and an angle to the left. So if we take a positive plus a negative, that'll give us an angle to the left for the I angle. So now we have for our curve here, we know something about where it starts and something about the central angle of that curve. Okay. But we still need another curve attribute to fix that. We don't know what the distance is from here to here. If we did, that would be the tangent distance. Okay. And now here's where we'll go into something similar to what Jen was looking at. But in this case, instead of going through the centers of the curves, what I'm going to do is I'm going to go up and down the tangents. So I know that the azimuth of this, if I like to work with azimuths because then I don't have to worry about whether I add or subtract latitudes and departures. It just automatically comes out straight out of the trig functions. The azimuth of this is 145 degrees. And here, the delta angle here is 63.45 to the right. So that we add that and that gives us the azimuth here. We subtract this angle because this is to the left and that gives us the azimuth of this line right here. So now we have azimuths all the way through here. We know that this is from here to here is T1, from here to here is T1, from here to here is T2, and from here to here is T2. So if I compute my T1s and my T2s, that'll give me my distances here. I can now compute coordinates here. If I start up here with, I assume a coordinates of 2,000 and 1,000 here. I go along at this direction at that azimuth, that distance T1, that gives me the coordinates here. Then forward calculation here to get this, forward calculation to get this, forward calculation to get this. And then I got that far. I can get that far. I can't do this coordinate here because I don't know that distance. Okay? But now what I can do is a COGO intersection. I can do a this direction intersection to define that point right there. Because I know the coordinates here and I know the direction of this line. And that's the direction of this incoming tangent. I know the coordinates here because I just computed them back here. And I know the direction of that line because I computed that going up and down the tangents. I can do a direction intersection to get that guy right there. And if you're not familiar with or a little rusty on the mechanics of a direction intersection manually, basically what you're doing is you're taking 2 points of known position and using them as one side of your triangle And then the other elements, angle would give you the other two elements of your triangle, and you would be solving for those. Again, if you look at the COGO portion on my website, I go through manual calculations of intersections like that. But anyway, so that gives me this point here. I get those coordinates. Once I have those coordinates, I can inverse between my PC and my PI, and that gives me my tangent distance. And from my tangent distance, then I can solve backwards to get my radius, which is 744.3. Ta-da. Is that what you came up with, John? Something close to that?
Yep, I got that.
All right, good. Now, see, you went at it a little bit differently, right?
Yep.
Because there's more than one way to solve a lot of these problems. Typically, with a regular COGO type of problem, where you're doing a distance intersection, or distance direction, or direction intersection, you have just enough information to solve the problem. And if you make a math mistake in there somewhere, there's really very little way to trap it. But in a problem like this, there's generally more than one way to get to the solution based on the logic that you're using. So which is the right way? Whichever way gets you to the right solution. Any other questions, comments on this?
Hey, Jerry,
Oh, and then I asked,
Jessica,
yeah,
Jessica asked, did other folks have the incoming radial direction missing from the problem? And Jen answered, I think you can assign it. It looks to me like, yeah, you can assign any arbitrary azimuth, any bearing you want to that incoming line to the first PC.
for which one? For the
Yes.
radial line or for the tangent line?
For the tangent line.
Well, the tangent line, it was given originally as South 35 East. I just converted to an azimuth.
Okay.
Well, I don't think we saw it given. If that was the question.
Wasn't it given in originally in the problem?
I don't see it.
Let's see. I'm looking at the hand. No, I guess it wasn't in there. I left that off. Yeah, well, in that case, it doesn't matter. See, I can rotate this whole thing 90 degrees. It's still going to give me the same solution. Yeah, I'm sorry. That was a mistake on my part. If I'd asked for direction of the long chord, then it would have been a problem because you need an explicit direction. Yeah, that's a typo on my point. Missing direction on problem E. Okay. All right. Okay. And I think there's one more, right? And then the other ones are just distances. Compute the distance from the PI to the for the PT to the PI. Again, once you've got the coordinates, you can do the inverse calculation between those. All right. All right, this is another one of those fun problems. Anybody figure out this one? How much area is in between the two curves and the tangent lines?
I got A. Does that mean
You got A. You got A. You get extra credit for working out all these problems. Nobody else did, huh?
Jerry,
What? Yeah.
do you use the formula for solving for like a sector to find that area? Am I thinking of that correct?
It's involved in the process. Yeah. Yeah. Because basically you want to break it up into geometric entities. Okay. Again, a couple of different ways to approach it, but the one way to look at it, and first of all, I compute the tangent, the eye angle, and the tangent distances because we have the geometry here. So we know what the delta angle is here. That's 85 degrees for the eye angle. And we can compute this tangent distance and this tangent distance using the tangent equation. And those are going to be basically those two numbers right there. Okay. Now, the way we can look at this is there's the area that's bounded by the tangent lines, the 200-foot curve, and the tangent lines and the radial lines for the 400-foot curve. There's also the area that's bounded by the 400-foot curve and its radial lines. If we take this area 2 and we subtract it from this area 1, That gives us the area in between the two. Okay. So how do we compute this area right here? Well, the first one, this one consists of two areas. Okay. It consists of the area bounded by the arc and its radial lines, which is the sector area. And also this area here that's bounded only by straight lines, which we can compute by coordinates, using area by coordinates. Now, there's actually two ways to compute this area. This is one using the sector, where I take out this piece of the pie here, compute that, add to that this area computed here by coordinates. The other way to do it is by using a segment area. If I take the area between the chord and the arc and add it to the area by connecting this point to this point to this point to this point down here and back again, computing that area by coordinates, I'll get the same exact thing. Just in one case, I'm using a segment, and the other one I'm using the sector. Okay. But in either case, I have all the information I need for that. So if I take that and I compute my third area, other area here is just the sector area. So if I take that sector area and I subtract it from the total area here, that leaves me at 20,948 or 20,950 square feet. And if I remember correctly, that was the first answer. That's what you came up with, right, Jen?
Yeah, more or less.
More or less. More or less. There. Do you approach it the same way, or do you use a different methodology?
Oh, no, not the same way. I found triangles. So I'm trying to figure it out from my notes, what I did.
Yeah, that's always tough.
When you sent it out. So it did involve finding the two different tangent lengths. And I think I found the small triangle and then the big triangle.
Right.
And then I used the small triangle and the segment. So I found the size of the segment, and I found,
Okay.
I think I found the big triangle and subtracted the small triangle. Basically subtracted the big segment and added the small segment, something like
Right.
that. Does that make sense?
Right. Yeah, because the triangles that you're dealing with, whenever you're dealing with curves, and the triangles are formed by the radial lines and the chord, that's always an isosceles triangle.
Yep.
And the area is always equal to 1/2 twice, 2 times the radius times the sine of the eye angle, gives you that triangular area. So it's really, really quick and dirty to calculate that. Law sines, law cosines, area of a triangle. I always ask my students, how do you compute the area of a triangle? And inevitably, they all say 1/2 the base times the height. And I tell them the next time they're home for Easter break or Thanksgiving break, to find a math teacher that taught them that and beat them with a stick, because that's a special case. That's when you're dealing with a right triangle. 1/2 2 sides times the sine of the included angle will always give you the correct area of a triangle. So it doesn't matter what combination you have, whether it's a right triangle or not. That's just a special case of the general equation for a triangle. The other thing I always warn them on, and I always give them problems on it, and it throws them for a loop, is when they do, let's see, I have here, let me get this back up here a second. When you're using the law of sines and law of cosines, and again, I go into a little bit in depth on this on my website because it's important. When you use the law of sines to solve for an angle, law of sines, if you have an angle that's greater than 90 degrees that you're solving for, your calculator will always give you the angle that's less than 90 degrees. It won't give you the angle that's greater than 90 degrees. So for instance, if the angle that you're solving for is 120 degrees, and you take the inverse sine of that number, it's going to come back with 60 degrees, not 120 degrees, because it normalizes everything to 90 degrees, 0 to 90 degrees. You always have to look at the angle and see if that angle is greater than or less than 90 degrees. If it's less than 90 degrees, then the way the angle comes out of your calculator is correct. If the angle is greater than 90 degrees, then the angle should be subtracted from 180 degrees to get the correct angle. So if it comes back with 60, and you look at the angle that's greater than 90 degrees, it's supposed to be 120 degrees. Now, if you've ever done any work with software doing Kogel intersections, and whenever you do a distance intersection, it tells you that there's only a single solution to that problem, because a distance intersection will only intersect at one spot. But whenever you've got a direction distance or a direction intersection, it tells you that there are two possible solutions. Why? Because there could be a solution for the angle less than 90 degrees and the angle greater than 90 degrees. That's why there's two solutions, is because of that law of sines. So whenever you use the law of sines to solve for an angle, look at your sketch and see what the angle condition is. Is it less than 90 or greater than 90? If it's greater than 90, take whatever angle your calculator tells you it is and subtract it from 180 degrees. Now, have I thoroughly confused everyone on that? Law of cosines, that's not an issue, because law of cosines, calculator doesn't normalize it to that, because your cosine goes from 0 to 90 degree, 0 to 180 degrees on the positive side, whereas on the sine, it only goes 0 to 90 degrees on the positive side, 0 to 1 degree, 0 to 1 for the sine of the angle. Again, it's explained in much better eloquence with examples on my website, so please take a look at it. There's a lot of trigonometry solution types of things with respect to using the law of sines and law of cosines. Questions?
I think you have a typo on that page too.
On which one? This one right here that's showing?
Um,
It could very well be, because I thought this got real quick.
right above the segment, square root of s times s minus a times s minus b times s should be minus c.
Right, yeah, it should be a -2. That's right. That's Heron's formula. Heron's formula.
And for our participants, sometimes we look at these problems and think, what the heck, why would we ever need to know this? And I got the peanut gallery in the background here. And so this could be a situation where the original alignment of a road has a curve of some smaller radius, and you're going to need to widen the road, flatten that curve, change the geometry of the road, and go to a bigger radius that flattens that curve and results in that difference in between those curves as your additional land acquisition, right? So you're going to be paying somebody for an acreage or a square footage, whatever the case may be. So sometimes getting the connection to surveying on some of these problems that we think, man, I've never run across this doing a subdivision. No, you don't run across it doing a subdivision, but you could doing a highway retracement or an alignment.
Right.
And that's what Dave and Rob Perez are dealing with day in, day out.
Right. And a lot of the stuff that you do encounter with doing the subdivision layout or design, they're all based on the same trigonometric principles as in these applied trigonometry type problems here. The solutions of law of sines, law of cosines. Now, you may be using a computer to do the heavy lifting for you, but it's still at some point the computer is asking you to make a decision. If you do a direction, distance, intersection, it says there's two possible ones. It says to you, you decide which is the right one. The computer's not going to decide that for you. By the same token, we also have to be aware of the fact that as we saw in some of these problems here, rounding becomes an issue. The computer or the calculator does a very good job of manipulating the numbers for you. But when it gets to the end to decide what is a realistic accuracy that you can express that to, that's up to you to decide. That's where the art comes in, along with the art and science of surveying and that type of thing. So, I mean, is it reasonable to express an area to the nearest hundredth of a square foot? Well, your setup error on one instrument, on one location is going to be that much, let alone expressing the area of a parcel to that. So it's still, you still got to be familiar with the concepts behind all these calculations to understand what results in that map being created in the end, in the first place. The other problems that I posted, these I have up on there also, that I added later. Whoops, let me move this over. I'm having a difficult time grabbing the top. There we go. If you can see this, these are again problems where you got to kind of think about what is being asked and what's being provided and what's being asked to compute and that type of thing, and what some of the relationships are that you know have to be enforced. Like, you know, if you've got a tangent curve, a line and a curve that are tangent, you know that the relationship here is just 90 degrees to the radial line here. It's 90 degrees to the radial line here. How do you use that information to solve for the problem? What do those curves have in common that one shares with respect to the other? Where are they unique with respect to that? So in this case here, and again, I got a typo in there, my goodness. It's asking, it gives you the geometry for this alignment here, and we're going to offset it by 19.5 feet, but we're going to decrease the radius of this so it's not as sharp, but it can't come any more closer than 12.5 feet from the other curve. This is actually an adaptation of a curve that was put into so that there'd be a certain amount of clearance between the curb line and the center line of a trolley that was coming through. So this is an application where we want to have a shallower curve, but it can't come any closer than this to the other curve. What's the radius of that curve? What's the maximum radius that curve can be? This one is a traditional one. I love these kinds of problems. What's the radius of an arc that's tangent to three sides? So you have three lines here, and you want to come up with an arc that's tangent to all three simultaneously. This one here, to divide an area in half by using a line coming through a pivot point. What's the length and the direction of this line here that divides this parcel into two equal halves? And then the last one, and this is kind of like what Rob was talking about a little bit here. This is an extension of existing roads into a new subdivision expansion where there's already the sewer, storm sewer, septic sewer that are in there. There's existing manhole, and a road is going to be put in, but it's got to be put in such that this manhole is located at the midpoint of the inner lane of the road that's going to go in there. So it gives you the information about the tangents and where the manhole is with respect to the PI. And we want to know what's the radius of the curve here that'll meet that condition. So again, what do we know about the geometry of those curves and how do they interact, and with respect to where this point has to be here? Most of these have a couple of different approaches to solving them. Right? They all have the same answer. I mean, we'll have the same answer, but they have a couple of different approaches as to how you would do it. These, I may post the answers to these later on at some point, depending on how many people I get sending me an email saying, what's the answer to such and such. But the complete worked out solutions for the problems I covered tonight will be posted on my website in a couple of days. So if you I didn't expect you to write down everything I was talking about here tonight, but you'll be able to see step by step what the calculations are to get to those. And I'll fix some of these typos that I have in there that snuck their way through. Any questions? Sean, did that answer your questions on those first two problems?
Yeah, it answers a lot of questions, and also it really helps to see the way that it gets set up, because for me at least, drawing the sketch really, helps in trying to solve these problems. So
Yeah, yeah. You want to draw a sketch, you want to draw it big enough where you can label things and see what they look like. And obviously having color helps a lot, but not everybody has the advantage of doing that. But when you go into the exam, be sure you take a straight edge with you so you can draw straight lines that are actually straight. Any other questions, comments, observations? If you do encounter, if you're going through review problems or anything like that, or you encounter otherwise, any types of trigonometric, applied trigonometry problems like this, let me know. And you need some help on solving them, I'll give you a hand. I'm trying not to resort to using calculus to solve some of these things, because some of these can be solved using applied calculus and that type of thing. But for the most part, 99% of the problems in surveying can be solved, or numeric problems can be solved using some sort of trigonometric or algebraic approach. Now, I didn't touch vertical curves with parabolic secondary polynomials and that type of thing. But I do have again, on my website in the vertical curves section, things on fitting vertical curves using going through specific elevations of specific stations and that type of thing. So if you want to see those types of applications, there are those there. And in addition, just as an aside, under the support files area on my website, I have a number of different Excel worksheets there for different types of surveying applications like COGO intersections, traverse adjustment, and that type of thing, that you can use those to generate your own problems to try to solve, or use them as tools to solve problems. So I'm putting in a advertisement here for my website. There are a lot of self-study problems on there too with worked out solutions. So feel free to, you don't have to register or anything. You don't have to have an account on a website to use it. It's all free. Yep. If there aren't any questions, any more questions, I guess that's it for tonight.
thank you very much, Jerry and Rob, for sharing that with us.
Hey, you're welcome.
Yeah, thanks, Jerry. You did a great job. There's some thank yous popping up in the chats, and I love watching these sessions and seeing how not only how the presenter has created the problems and found the solutions, but the way that the students or the participants come up with ideas to solve those. So I think that does it for us. Trent's still probably a good 45 minutes from landing at this point, but that should do it for this week.
Okay.
Thanks again, Jerry. It was really
Welcome.
cool, and I love your background photo.
That's where I grew up. This is the farm in northern Wisconsin, but
Nice. I imagine there was some fish caught in those rivers and lakes.
oh yeah, northerns and some walleye up in that area there.
Nice.
All right.
Nice.
Yeah,
All
thank you
right,
much,
folks.
folks.
See y'all next Monday, and get the word out. Let your coworkers know that this is going on, and that the recordings are usually posted up towards the end of this week. So I don't know exactly how many sessions we've got in the archives now, but I think it's close to 50.
Yeah.
So pretty amazing that Trent has brought this along with our presenters like Jerry and everyone else to out to you for no charge, just to try and improve our profession. So do your part, join your local and state professional society, and hope to see you at a conference in the near future. I know we're looking forward to Arizona, California, Nevada, Utah, and the Western Federation of Professional Surveyors all getting together at the end of March, beginning of April of 2022 in Las Vegas, Nevada. And pretty much no matter where you are in the country, you should be able to get a flight to Las Vegas. So come on down and sign up for those sessions at plseducation.org, I think it is, or californiasurveyors.org. I'm sure that's the right website address. So thanks again, Jerry. Hope to see you soon. Take care.
Mhm.